Good evening, ladies and gentlemen. Tonight, we're going to hear about Asteroseismology and Starquakes. I think most of us here have experience or knowledge of earthquakes. Many of us also would have experience of using seismic techniques to probe the interior of the Earth. But I think very, very few of us know about starquakes and examining the interior of the stars above us. So we're really lucky tonight to have a world expert on this subject who's going to take us through this interesting topic and explain not only how we can look inside the stars, but also how this helps us understand the galaxy in which we live. It's a pleasure to be able to welcome Professor Conny Aerts here tonight. Conny is a professor at the University of Leuven in Belgium and has a professorship also at the University of Nijmegen in the Netherlands. She has a long and distinguished and prize-winning career in the field of physics of stars, especially Asteroseismology, but she also, in her career, contributes enthusiastically to astronomy in general and to advancing the cause of women in astronomy. Let me very briefly take you through her career. Like many professional astronomers, her interest in astronomy started when she was very young, still at primary school. She continued then on a route many professional astronomers take, doing a degree in mathematics at the University of Antwerp, and then moving on to study for a PhD. For her PhD at the University of Leuven, this involved travelling to many international observatories and taking high-resolution spectra of stars and then using advanced mathematical techniques to analyse them in order to determine the oscillations, the wobbling and the vibration of the stars. And some of the techniques that she developed then are still in use today. After her PhD, she won a grant to do research to establish her career, to establish a research career. And then if you read Conny's biography, she says, probably with a typical smile, she started off this work with a 5-month leave of absence to have her first child. So when she came back, she positioned herself in a slightly broader field, variable stars, to exploit the data from one of the satellites of the European Space Agency, the Hipparcos satellite. She was appointed a lecturer at Leuven and then a full professor, and also has a full professorship, as I said, in Nijmegen. The research of Conny and her team covers a very broad field about the structure and evolution of stars. And to do this, she looks at many different stars of different ages, different chemical compositions, and different masses, and pays particular attention to their oscillations. It's a very vibrant field with lots of new data, and she's published, and with her team, many groundbreaking results, including, for example, on how the stars rotate internally. And her research was recognised in 2012, just 2 years ago, by the award of the very prestigious Franke Prize, which was presented to her by the King of the Belgians. This prize is awarded annually and to recognise the achievements of a Belgian scientist or scholar and to encourage future work, I understand. And Conny was the first woman to receive this prize in the exact sciences. I was searching the history of the prize, and it's interesting to note they've not yet caught up with. Most of the websites still refer to the recipients, the laureates, as he. So following you, they're going to have to change that. This prize is often referred to as the Belgian Nobel Prize, and looking at the list of past recipients, I note that several of them also got Nobel Prizes. So Conny, no pressure, no pressure. So looking at your other activities, quickly moving on, she's always been willing to give back to astronomy. She's served as president and vice president of various commissions of the International Astronomical Union, the governing body of world professional astronomy. She serves on many national and international committees, and that's actually how we first met. We first met about a decade ago when she was advising the European Space Agency on one of its committees. And I remember vividly not only her forthright scientific opinions, but her determination and her ability to smile and make the room look happy the entire time, even when there were major disappointments, like ESA not being able to go ahead with a mission in her field. I mentioned earlier her determination to advance the role of women in astronomy. In her own institute, she's achieved an equal gender balance, which is much better than astronomy as a whole. I've been working with her over the last few years on setting up research workshops, and with every proposal, Conny first looks at the science. Is the science good? Then her next question always is, are there enough women involved, both as speakers and as organisers? And if not, she's extremely determined in making sure the organisers fix it. Also, I mentioned her role in the IAU, the International Astronomical Union, and there she was interviewed for a blog known as She is an Astronomer. Do you remember that? And at the end, the last question the interviewer asked her was, what recommendations would you make to young women starting their career in astronomy? And there are several very nice ones aimed at women, such as don't adapt to men's style, make them adapt to yours. But there are also ones much more general, which I think sum up Conny as a person. Do it your way, even though it's different from all others. And make sure you have a good personal mentor and follow the advice of good role models. So to finish, Conny, it's a pleasure to introduce you. I'm very pleased that with the recent selections in the ESA Science Programme, I think there are a lot of missions that are interesting to you and we can work together. And so may I turn the floor over to you to talk to us about Asteroseismology and the study of Starquakes and their impacts on astrophysics. Professor Conny Aerts.
Thank you very much, Martin, for this very generous introduction. And to the audience, I'd like to say it's my pleasure to be here and to be able to discuss about one of my passions, which is also my work, and that by itself is already very pleasant. So I'm hoping to bring you up to speed and make you all expert asteroseismologists in 1 hour. That's my task, assuming that you are not yet familiar with this field. So here you see what this talk will be about, and I tend to speak of starquakes because in fact, as Martin already alluded to, everybody is somehow familiar with earthquakes, and earthquakes are used to study the interior of our planet. I cannot start drilling a hole here until I reach that core of the Earth, but I would still like to know what's inside it and how it will evolve, because that's of general interest to everybody. So we are going to do the same for stars. Stars that are really billions of kilometers away from here. So as you can imagine, it's a bit more difficult to detect these starquakes. But we can do a lot with them once we do. So let's move on. You know, this goal of this study is to learn about how stars live, how they get born, how they live their life, and how they die. And we want to understand that, and we know that fairly well. In this upper plot here, you see a sort of a cartoon of how the sun will live its life. So it gets born from clouds of molecules when they collapse under their own gravity. That's the general way that stars form. Then it lives a quiet life for about 90% of its time, and we're about halfway. It's just for you to know that you need not be worried about what I'm going to tell you, because there will be some less nice episodes in the life of the sun, but you will all be dead. So there is no need to worry, and also your grandchildren will probably no longer be around, because we're talking about evolutions in billions of years. And this already tells you why astronomers have to be clever. We are frustrated. We cannot watch a star, how it lives and how it dies. because it simply takes millions to billions of years. So we have to find a way to understand stellar evolution by looking at different stars in different evolutionary stages. And so at one point there will be a really global warming going on. Not tomorrow. This is not about global warming of the Earth. This is about global warming of the Sun with respect to Earth. And this is an artist's impression of what will happen. At a certain point, the Sun will have no longer nuclear fusion in its core. Stars, they are experts in nuclear fusion. We can't do that in a safe way here on Earth, but the stars have no problem with it. And that's in fact what directs their life. That's what gives them the energy that you can see with your eyes when you look at the nightly sky in the evening. At a certain moment, the fuel is finished, and so the star will start dying, if I may say so, and it will swell up. So the Sun will come very close to Earth, and it will be much hotter, even though Madrid was, for us Belgians, the past few days, very, very nice and hot. But this is beyond any comparison. And so we want to know how this path here goes. We want to know the details. We know more or less how stars live. We also know that some stars get born with a very heavy mass, and they will end their life as supernova explosions, big explosions. Again, nothing to be worried about because there are no such stars in our close vicinity. So we will see the explosions very far away. Stars like the Sun, they will have a very quiet death, but they will swell and become what we call red giants. And that's what's going to happen to the Sun. And we have been studying a lot of stellar quakes of red giants for this reason. Now, why do we want to bother? Because I just told you in a few minutes how stars live, so we already know. But, you know, there's an expression in English, the devil is in the details. And it's the same for stellar evolution. We can't look directly inside the core of a star, and that's where the life is being determined. So we would very much like to see inside the star, but we cannot. We only see the surface of the star, and even then, the stars for us are tiny little dots in the sky because they are so far away. So we cannot resolve the stellar surface, let alone look inside. This view is blocked from our observations. And this is bothering us because we know that the theory has shortcomings. We know, for instance, that there are massive stars like this cartoon here is trying to depict, where the life of the star seems to be longer than our theory predicts. So that's because there is not enough fuel in the core of this star. So this core region here, where the nuclear fusion is taking place, and it's only in the core because nuclear fusion needs a very high temperature and a very high density. And so these quantities, they go down as you go away from the core, and then it's too cold to have nuclear fusion. Well, we know that we are lacking some material inside this core, and we need to understand why that is. Also, and that may be good news for us, in the recent years, a lot of planets have been found around stars. These are called exoplanets. And so these planets, of course, we want to know, are there many? Are they like the Earth? Are they more like Jupiter-like gaseous planets, and so on? But what has struck us is that some evolved stars, some red giants, so some successors of the Sun, while they are dying, they have sort of still planets. Well, if our theory would be correct, the planets should have been swallowed because the stars would have eaten them up. And so that may be good news for the Earth, but it also tells us that our theory is not really adequate at this stage. And so we want to improve upon that. And how can we do that? Well, as I said, we only have observations of the stellar surface, so we would like to do something better. And then I come back to the seismologists, the geophysicists on Earth. We only have measurements at the surface of the Earth, but we would like to do better. And what they do is use their seismographs to detect the earthquakes, and this provokes waves, and these waves travel all the way to the Earth core and bounce back. And so then they can be detected again. And by doing this inference, we can learn about the core of the Earth. And we are doing the same for stars now. So how does that work? Well, I love mathematics, but I might be correct in thinking that the majority of the audience is not really an expert in mathematics or in physics. So I didn't bring any equations today, only cartoons to get you onto speed without mathematical formula. So why do we do seismology? How does it work? Look at this here. Let's imagine we could cut a star into 2 pieces, and then the starquakes, the oscillations, they would invoke waves, and they are indicated here in the slide in color. So you have this red wave, and you have the green one, and the yellow one, and so these quakes, they give traveling waves that pass through the star. And me, as an astroseismologist, I would love to detect, well, the red wave's okay, the green and the yellow one are also fine, but I love this purple one. Because that quake gives a wave that passes all the way through the stellar core. And that's where all the action is. That's where the life is determined. So we want to hunt for these purple ones, but it's already a success if we can detect anything at all. I'm sure all of you, hopefully with protected glasses, watch the sun every now and then, maybe at sunset when it's not so strong for your eyes. The sun has hundreds and hundreds of solar quakes all the time, but you can't see that because the quakes of the sun have too low amplitude. Your eyes are not good enough detectors to see that. Yeah? Because the amplitude of these quakes are parts per million. And your eyes are excellent detectors, but not good enough for this. Okay? So that's what we have to try and detect. Now, how does the mathematics work? Let's follow this yellow wave here during many cycles, up and down and bouncing back. This is like traveling sound waves in an auditorium. Right now, I'm making a lot of sound waves, right? And the technology helps me a bit here. And you can hear me, even if the microphones would be dead, you would still hear me talk because I create sound waves and they travel in this cavity, in this beautiful room here. It's the same in a star. You know, the star is a gaseous sphere, it has quakes, and that's comparable to sound waves. And by understanding these sound waves, we can understand the physics. Because the way the sound propagates is determined by the pressure and the density and the material of the cavity, let's say, of this concert hall. Yeah. So let's say we follow this yellow wave and we follow the green one, and let's assume that we have a way to detect their effect on the surface. Well, it's the same physics, right? It's the same star. Only the green wave goes a bit deeper than the yellow one. So by subtracting the frequencies of the waves, we learned something about the area in the star that's only green and not yellow. And so if we have enough waves, we can build up the interior of the star layer by layer in terms of its physics. And that's basically how astroseismology works. And in daily life, I don't use the pictures, but I use the equations. But it's the same, okay? So, to give another analogy, which you may be very familiar with, and if I give this talk to very young kids, it always works. Huh? I hide myself after the screen, and then I play a flute. And I won't do it today, but I did bring it. I play a flute, right? And then I ask the question, what is it that you hear? And then they all shout, a flute, because they are proud that they can answer a professor. Right? And then I disappear again, and I play another instrument, which is a piccolo flute. And then, of course, I ask the question, which flute is the biggest one? The first one or the second one? And they all have it right. Because this flute has much higher tones, right? The smaller the instrument, the higher the frequency. You all know that. So that's what we do with stars, only we can't hear the stars. The sound waves invoked by the quakes of the stars, they remain inside the cavity, they remain inside the star. So that's a bit of annoying, because else you could rely on your ears to decide about how big a star is and how small. It's just like with the flutes, okay? So what do we do in practice? Well, here is a very, oh, I went too fast here, let me go back. Here is a very simple musical instrument, let's say a guitar string, and the musician knows perfectly well, if he or she has a symphony in front of him to play, how to deal with this. He can play the string in the fundamental modes, or in the first overtone, or in the second overtone, or the third one, and so on. Yeah? So what do you do when you characterize a string that is vibrating, that is oscillating, that is having a quake, if you want to use that terminology? You need a period, that's the frequency with which this string goes up and down. You need an amplitude, that's the strength of the sound, let's say. And you need a number, and the number indicates how many notes you have, how many overtones you have, okay? So let's now move on to a star. A star is just, for me, a three-dimensional string that plays music, right? And so what do we need? We need a frequency for each mode. We need an amplitude, that's the strength, yeah? And we need three numbers, because we're now doing it in 3D. But for the rest, it's the same. So the mathematical description is really very, very similar. And so here you see three stars. These are not real stars, these are animations, of course. And so instead of knots, we have nodal lines, because it's a two-dimensional surface that you're looking at now. So all the particles in these white bands here, they do not move during the quake. They stand still. These are the nodal lines, as we call them, instead of knots, okay? So in principle, asteroseismology would be simple if we could resolve the stellar surface, because we could just see it moving up and down. But we can't do that. We can only do that for the sun. For the sun, we can resolve the surface, and that's why the study of solar quakes, which is called helioseismology, has been developed much earlier than asteroseismology, where we have to do the same kind of trick, but then for stars that we cannot resolve, okay? So, still, I would like to come back to music, because that's very clear in your mind, I think. And I'm not a musician, so I can't play a concert. But anyway, let's move to the analogy. And I would like you to sort of get a grasp of how stars would sound if you could sit in their interior. It's not a nice place to be. It's far too hot there. You don't want to be around. But still, I want to give you a grasp of what it would sound. So let's look at stars as musical instruments for the time being. And again, here is my very simple example. You have a normal violin. Let's compare that to the sun, right? Well, then you know if you are going to play this instrument, or the contrabass, let's say, the bass will have much lower frequencies, yeah? Okay? Now, we can't resolve stars. So what do we do when we study star quakes? So the surface is going up and down with a specific frequency and amplitude. And in the interior, it's also bubbling, let's say, but we can't see that and we can't hear that. So we have to do something about it. We can see that if we have a very good detector, much better than our eyes, and we can build those detectors. But then we still have to observe the light of the star and how it quakes. And here you see a seismic determination, or measurement, I should say, in time. And so the surface, the luminosity of the star is not constant, because it has these quakes, you know. And if at a certain moment this is gas, so this moves much easier than the crust that we have here on Earth, if that material moves towards the interior of the star, it gets a bit hotter, so it is brighter, right? If it expands, it's a bit cooler, and so we see less luminosity, less energy. And that's what you see here in time. And so the way this changes is directly connected to the frequencies of the oscillations. So from measuring how the brightness of the star changes as a function of time, we can derive the frequencies. Even though we can't hear the sound, because the sound can't travel from the star to us because there's no material, right? There's a vacuum. The only thing is that, you know, this is, as I said, parts per million. While if I go to an observatory here on Earth, and even the best ones, and Spain has some of the best ones, I'll come back to that later. The transparency of the Earth atmosphere, the disturbance, is typically parts per thousand. That's really annoying. Even if we are in the best places, the Atacama Desert in Chile is typically an example. The Earth atmosphere is bothering us in this science. So how did we come to make progress? Thanks to space missions. And so I'll come back to that later. But let's first hear those sounds, because it's just fun to listen to them, okay? So, cosmic symphonies is what I tend to call them. These are starquakes, and the waves they introduce, and that you would hear if you were inside the star, where you can't be, but I'm going to place you for just a minute inside the sun. Yeah. So we're going to pretend as if we're inside the sun, and then you can hear the symphony of the sun. But unfortunately, I have to do another trick, because your ears are not sensitive to the frequencies. Yeah? So I have to shift the symphony of the sun as we measure it through these light variations. I shifted that to make you able to hear it. And then you can listen to the symphony and decide for yourself if you like it or not. And so if you are pleased or not by the fact that we can't hear the stars in their orchestra, let's say. Okay, are you ready? This is probably your first cosmic symphony. Is that nice? Are you happy we can't hear the sun? It's not nice, huh? Except for artists in artificial music. They love it. But it's the real sun, except for a factor 1,000,000. Yeah? And so what you see here is what I tend to call the symphony of the sun. So you see here a graph, which gives the strength of the solar quakes as a function of their frequency. Okay? And you see here, all these black lines here are musical tones that are connected with specific quakes of the sun. And what you see is that the maximum strength occurs at a frequency of about 3,000 microhertz. And if I turn that into a periodicity, then that's about 5 minutes. So the solar surface goes up and down with periodicities of the order of minutes. Okay? And so now I'll move you to another type of star, the star that the sun will become in 4 billion years from now. This is going to be the star that is going to eat the Earth. Right? It's going to swell up. It's not nice, but that's the way it is. Yeah? And so what's going to happen, I'm saying that it's going to swell up. That's moving from a piccolo, which is the sun, right, to big flute. So you know what's going to happen with the sound. We're going to go lower in frequency. Okay? So I again multiplied with the same factor 1,000,000 to make that comparison possible. So now we're going to move to a red giant symphony observed by the Kepler satellite. Kids love this in the discos. Every open day we have a big success, because it is a real star that you're hearing. We only cheated a bit with the factor 1,000,000 for your ears. Okay? So let's look at this symphony now. Strength of the quakes as a function of frequency. Remember, the sun peaked at 3000 microhertz, and we're now peaking here somewhere, say 65 microhertz, much lower. The star is much bigger. The instrument is much bigger, okay? So we don't listen to these sounds, but we do, day by day, analyze such diagrams, yeah? Because they come directly from the measurements. And now, of course, to complete the story, in the end, the sun is going to die as a really small, cold body, which we tend to call a white dwarf. Huh? And so we're going to listen to a subdwarf star, which is a very tiny little small star. And then you know what's going to happen. If we shrink, then we have a smaller flute, and the tones are going to go up, okay? Higher frequency. These are data that I have taken at the Canary Islands in La Palma. I'm very grateful to Spain for having that opportunity to put a telescope there. This is a subdwarf, okay? High frequency. So we can do these measurements from the ground, but the real revolution came as soon as we had the space missions. And these are unmanned space missions, just to be clear. Sometimes I get that question, when do you travel, when do you come back? We don't travel. We travel to exotic places, but not to space. Huh? And this is a cartoon of the CoRoT space mission. That's a French-led European space mission, launched in December 2006, and it was operational until last year. And this is the launch of the NASA Kepler space mission, which are the two instruments that really help this science to get a boost. And so here is an example of what I do in my daily scientific life. It looks like a complicated slide, but I'll get you through that. We get these nice uninterrupted data from space. Why have I highlighted the word uninterrupted? It's crucial, because we can do seismology from the Earth, as I have just given you an example, but then we must interrupt the data taking during the day, because it's light. The stars are there, but we can't see them. Okay? So we have to cut this variation in the time series day by day. So you introduce a rhythm of a day into your measurements, and that's really annoying for us. So uninterrupted space data, the satellites, once they are launched, they don't care about day and night. Yeah, they have no problem with that. And that really helped us a lot. And then factor 100 better precision, because we bring the satellites across the Earth atmosphere. So we don't have any problem with the disturbing factor that we have at observatories. Then we do mathematics, because here is a seismic measurement in time, you know, expressed in days, as you see here. And you see all the quakes of this star. And the gray band here would be the stellar light if the star would not have quakes. So then it would be completely stable. And you see all these excursions here with a blow up in between. And then we translate this by mathematical techniques to this strength frequency or strength period diagram. And all these black lines here are the tones in the symphony of the star. Okay? So then we made the step between you know, not being able to hear, but being able to measure the brightness variations. And so as you see, this is quite recent that we can do that. Now, let's look again at the sun. You have heard the sun. You know more or less. It's a bit boring, frankly, if I may say so. This is the symphony of the sun. And these are two stars measured by the Kepler satellite of NASA that are very much like the sun. So they are sort of copies of our sun, so we want to understand if they have the same physics, because that's quite relevant for us, since the sun is determining our life as well, okay? I don't know if you can read it, but here you see the maximum strength near, well, 2,200 microhertz, more or less. And here, well, a bit more than 2,500. Yeah, the sun had its maximum at 3,000, So this is a bit lower frequency, but only a tiny little bit. The red giant had only 70 microhertz. This is still very close to the sun, but not an exact copy of the sun. These stars, if we look at them from classical data, without any quakes, are exact copies of the sun. Because we can't look in the interior, because we don't have the quakes. Stellar quakes tell you immediately a much better handle on the physics, because we can see slight differences in the waves that propagate. And what does that mean? Well, the frequencies of sound waves, like I'm producing right now, they depend on the pressure, the density, and the temperature of the gas inside the star. Yeah? And you see that this is not just a random set of black lines that you see. It's very ordered, it's very structured. Yeah? So this because the star quakes go according to eigenfrequencies of the body, as we say. Yeah? And so you see that with the other stars as well, so we get a good handle on how that works. And you see that there are patterns here, regular spacings between these peaks where they occur in frequency. And from this we can deduce information comparatively to the sun on density, temperature, and so on. Now, you can't probably see it in this graph, but some lines are thicker than others. I don't know if you can see it in these two stars. This here, for instance, this is thicker than that one. Yeah? That's because there's a tiny adjacent line, a tiny adjacent musical tone close to it. And these frequency separations are tiny, and so we need a long time base of measurements to be able to deduce them. And these are connected to discontinuities in the sound speed. So if I were to swallow or inhale some helium gas, which I sometimes do, and I would keep on talking, then my voice would all of a sudden change frequency. It would be funny. Yeah? So frequencies change according to the material of the musical instrument. And so in the core of a star, you have nuclear fusion. And so the sun is right now transferring the simplest gas that exists in nature, which is hydrogen, and it fuses that into the second simplest gas, which is helium. Right? And so where there is helium, the waves propagate in a different way. And so the helium core, when a sound wave is coming and crossing the border, it all of a sudden has a hiccup, because it needs to pass an area where the density is different, the temperature is different, and the chemistry is different, okay? And so these small separations tell you where the position is, where the chemistry is different. And remember, I told you we wanted to know how much material was in the nuclear reactor. And astroseismology can give us that for this reason, because the propagation of the waves all of a sudden is different. Yeah? And so, if we know how much helium there is in the core of a star, we immediately know the age. Because that tells us how long the nuclear reactor has done its work. That determines the amount of helium. And the lucky thing is that we have a calibrator, because of course you need some kind of calibration. Huh? And the calibrator is the sun. Because we know how old the sun is. We know that from totally different techniques than helioseismology. Huh? I'm doing the helioseismology, but the people who study meteorites, they tell me how old the sun is. They also tell me how old the Earth is, more or less. Okay? So we have a totally independent measurement of the solar age from helioseismology, I should say, and from other means. Radioactive techniques are very helpful. And then we can see how the match is. And the match is better than 0.1%. So we have a fabulous age estimator from this. And determining the age of a star is really hard if you have no astroseismology. You basically can't do that. No. So this is really helpful. Now, this is the result from the Kepler satellites. So for the sun, we had been able to do helioseismology and set up the whole techniques in mathematics and physics to make the framework, let's say, and that was done in the 90s. And here's a diagram of energy output versus a measure for the surface temperature of a star. Huh? And then you see here, this tiny dot here where my green laser pointer is, that's the sun. Yeah? And the sun has a surface temperature of about 5,800 degrees Celsius, right? Very hot. Huh? And now all these stars, all these dots are a star for which through the Kepler NASA mission we have been able to do asteroseismology. That means we have a radius estimate. Remember the musical tones, big flute, small flute. We know immediately how big they are with a precision that is impossible to reach without these measurements. We have a mass. We know the material inside the star. We have a good temperature estimate. And we have a good handle on the chemistry of the star inside the star. And this is unique. We couldn't do that before. And then came another breakthrough. This was already achieved by the CoRoT satellite, which came before the Kepler satellite. CoRoT is a smaller telescope compared to Kepler. So the data have lower quality, but still magnificent compared to data from the ground. And here we could already detect red giants, which are successors of our sun. So this is what our sun will be like in the very far future. And we have all symphonies. So each telephone number here is a star. We have to give numbers to stars because there are too many. So they have very boring, long numbers in our catalog. And here you see a power spectrum. And look at this. Here is the power maximum. Here, 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 here. You see this shifting? We are simply witnessing stars. Let me give this. Normally I do exams in between my lectures, but I will not bother you with the details. The maximum here is about 70 microhertz, right? And we move all the way to lower frequencies. We go from a big star, which is called a red giant, to an even bigger one, bigger one, bigger one, bigger one, as we go from the bottom to the top. So we are watching stars grow old here. And remember, I told you in the beginning, we can't do that if we pick one star, because it takes billions of years. So by studying ensembles of stars, we can do that. Huh? And so what do we get? What we got from the CoRoT satellite was that red giants have quakes. We didn't know that. And this came as a very nice, well, I wouldn't call it surprise, because in my opinion, all stars have quakes, but we hadn't been able to detect them. So this opened up astroseismology for a whole bunch of stars. And then came Kepler, and here is a press release picture of 4 red giants, quakes. This is time, a slice of 20 days, and this is a big red giant, even though it looks like a small star here on the screen. That's because it becomes, as it grows older, it becomes bigger and bigger and bigger and so on. And you see that if you don't like to work with these frequencies, because that's maybe a bit too mathematical, you can just watch the luminosity of the star change. So that's the brightness change that you see. This star has this brightness change. We move all the way up. What do you see? The brightness fluctuations become bigger. The quakes are bigger. The star is bigger, so it oscillates longer. And not only that, the recurrence pattern, the periodicity of the quakes is stretched. It's as if I had pulled the time axis, right? The frequency is lower. It takes the waves longer to travel through a big star, okay? So from that, we can set the size of the star and the age, and this is magnificent. This is something we had wanted to do since very many years, and we couldn't. And then came another big surprise, because up to now, I've told you about sound waves invoked by stellar quakes. But some stars in the red giant family, they happen to have a bit of different quakes that do not only feel or behave like sound waves, but that they feel the buoyancy force, as we call it. Now, this is a difficult term, but I can easily explain that by the analogy if you are at the beach somewhere, and you know, you have the ocean, the sea has quakes, right? And these quakes do not go up and down like that, but they more or less horizontally have wiggles. These are what we call gravity mode quakes. They are determined by the gravity force. And if you combine the two, so you get sound waves, you get buoyancy waves, the two combined are what we call mixed modes. And the advantage of these mixed modes is that they propagate all the way to the center. These are the purple waves that I showed in the beginning. We have them, finally. We got there. And this is an immense privilege because these purple waves, they probe the stellar core. And that's where all the action is. So, thanks to these mixed modes, and they don't give that, normally the patterns of these red waves, the acoustic waves, in such a diagram, and you can't even read the axis, but it's not so important, you would have clear ridges. And so all of a sudden, these type of modes, there should have been a ridge if it was only a sound wave, but it's a mess. The star is sort of playing